Well, it's time to wrap up those ISIS concepts as we look at part 2, an in-depth look at how ISIS works. We're going to get into well, I guess the feared part of ISIS, and that's the NSAP addressing. One of the things you have to do is assign your routers an address from the OSI protocol stack. We'll talk more about why that is in just a moment, but that is one of the big things as to why people are like, ooh, I don't know if I want to use ISIS because of this NSAP addressing. We'll look at how to apply that address to a Cisco router, how ISIS routes packets once we do have a domain up and running and we're sending packets between our devices. Then we'll look at the ISIS packet types. Just like we had in OSPF, the different types of packets, the LSUs, LSAs, and that sort of things, we have different ISIS packet types, and it's actually much easier, thankfully. And then finally, we'll look at the ISIS network types. Also much easier than OSPF. You remember those 5 network types that we had just for an NBMA cloud? Yeah, not here. Very, very simple. Boiled down to 2 network types. So let's get going. Well, let's start off with this NSAP addressing. We'll look at the facts of what these NSAP addresses are. The fact is that OSI uses these things called connectionless network protocol addresses, or CLNPs. That's the equivalent of IP in the TCP/IP protocol stack. It's connectionless, it's unreliable, it's just a protocol that puts a source and destination address on there. Now, CLNP addresses can be assigned to a router, but when you do, they change names. Whenever you assign a CLNP address to a router, they call it a Network Service Access Point address, or an NSAP address. That's where this NSAP comes from. And when you apply it to a Cisco router with a special code on the end, they also call it a NET address. You can see all these terms just kind of blending, like what's the address? What is the address? I would say it's safe to say NSAP addresses and NET addresses are essentially the same thing. You can really just put an equal sign in your mind. Now, the beauty of OSI and the beauty that you have to deal with when you configure this is that it's one address per node, or in our case, one address per router. We do not have to assign an NSAP address per interface like we do with TCP/IP. Now, this address is going to identify not only the system that it's on, meaning kind of like a system ID, this is my address sort of thing, but also this address will identify what area that router is in. That's why this address is so important. And it's almost like I feel like I should have said that early on. This NSAP address is important because this will tell the Cisco router what ISIS area it's in and what system it is, or I guess you could equivalent that to the OSPF router ID, what router ID it is in that system or in that area. Now, this is where the difference comes in with OSPF. The NSAP address can be up to 20 bytes in length. Compare that to an IP address that's only 4. Remember when I said we were looking at TCP/IP versus OSI early on, and they said, well, who would need that many addresses? That's because OSI addresses can go up to 20 bytes. That gives you a lot of addresses. So these NSAP addresses can be longer and most likely will be longer than your typical IPs. Now, the OSI protocol was designed to be big, really big, and scalable. And the original implementation of the NSAP addresses defined more than 5 fields, or I guess it'd be easier to say 5 sections that it would categorize into. And to compare that to what we know, if you look at an IP address, that divides into 2 sections. You know what they are? Network and host. Right? Our subnet mask says the ones where the 1 bits are, that represents the network. Where the zeros are, that represents the host. Now compare that with the OSI protocol. Whew, 5 sections is what we're looking at. Now, thankfully, you don't have to get into all 5. Cisco implements it with only 3 of those sections that are being used. Now, that's because those 3 sections are what the Cisco router needs to run ISIS, to interoperate with this routing protocol. Those fields identify the area, identify the system, and identify something known as the NCell. Now, look below. Take a look at the example address I have here. This is an example address. This is actually a typical address that you might see assigned to a Cisco router. First thing I need you to see. It's hexadecimal. So we have letters and numbers that are in our capabilities. And in hex, you'll get to deal a lot more with hex in IP version 6. But in hex, every 2 digits or 2 characters represent a byte. So this is 1 byte. This is 2 bytes. This is 2 bytes. You see what I mean? So this is 1, 2, 2. So that's really how we look at the bytes in hexadecimal. So with that in place, this address, this example address, can actually be divided into the 3 parts that you see right up here. This represents the NSAP selector, the N cell. Now, what that N cell is just an identifier to say this is a router. I can tell you this with confidence. Every NSAP address that you assign to a Cisco router will have the last 2 digits of 00. Always. Always 00. Because that N cell, that NSAP selector, tells what kind of address this is, and 00 represents an address that is assigned to an intermediate system, or in our language, a router. Now I'll tell you right over here, these next 3 sections, chunk, 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 all represent the system ID. And this represents, oh, my pen ran out here, represents the area. Now, how did I know that? How can I look at that address and just chop it up into little pieces like that? Well, let me show you. To understand how I did that, you have to understand the rules of the game. The rules of NSAP addressing, just like you had to learn basic rules of IP addressing. The NSAP address can be 20 bytes. And if you think about every 2 characters equaling a byte in hexadecimal, that can be a really long address. I mean, think of it, about 40 characters in length before you max out. Now, the second rule of the game is that the last byte of the address is always 00, which represents an IS, an intermediate system or a router in the OSI world. So, as I mentioned, we will always have this last byte right here being 00 on our routers. Now, the way Cisco has implemented this on their systems is the system ID, the identifier of the router, or to compare this to OSPF, that's like the router ID. The router ID is always a fixed 6 bytes in length. So if you were to remember that every 2 characters equal a byte, we'd have 1, 2, 3, 4, 5, 6 fixed 6 bytes in length that are going to be identifying the system, and then whatever is left over represents the area. I want to put this in perspective because I want you to learn how to read these addresses. The best way to read them is right to left, because here's the key: what you know is right. Does that make sense? No, not at all. The stuff on the right is what you know. You know that all the way to the right, you will always have 00, right? Right. You know that after the 00 will be 6 bytes. It has to be 6. It can't be smaller. It can't be larger. It has to be 6 bytes of information, and that will be the system ID. Everything that is after that represents the area. So you might be looking at this example and saying, well, that's kind of weird. Does that mean that area is 49.0003? Sorry, I got an extra dot in there. But the answer is yes. This means this area is 49.0003, or what is left over on that address right there. Do you see the problem if you read left to right? If you know that this thing can go up to 20 bytes, I mean, this is just a small address compared to what we could have. And if you go left to right, you don't really know. The area length isn't fixed, so you don't know where the area really ends and the system begins. So that's why it's best to go right to left. Now, there's another address that's out there that is 6 bytes in length that we run into every day in the network world. Do you know what it is? It's a MAC address. MAC addresses are 6 bytes in length. So because of that, administrators commonly make the MAC addresses, one of the MAC addresses on the routers, to be the system ID. because the system ID has to be unique in this whole system. You can't have duplicate system IDs. This, what you see on the screen right now, is something that I do a lot in lab environments, and actually something I did on my CCIE lab exam when I took it. I made the system ID of the router equal the router number. You know, in labs, you usually don't name your routers. You usually have like router 4, router 3, and so on, right? So I'll make the system ID something like 44444, you know, something I can look at and go, oh, well, that's obviously router 4. So that keys me in into what that router is. But system IDs do have to be unique, and you can see right here, this is 490001, area 1, I guess you could boil it down to. Those two routers share the same area. This router is in area 2, or 49002, and then this router's in 49003. Now you might be thinking, Jeremy, what's with the 49? Why didn't you just put 3 or 2? Why'd you make it complex like that? Well, that is not a how should I say that? It's not required to put that in front, but it is considered a best practice because 49 in the OSI world represents, and see the similarity here, a private address. Just like we have private addresses in IP version 4, like the 10 network, 172.16 through 31, and then 192.168 networks, those are all private. Well, a private address in OSI is this, 49. Now, it's truth to know that we're not going to run into conflicts with public addresses, right? I mean, obviously, OSI did not take over the world. There's not this internet-sized region where we're running into address conflicts, so you can use whatever you want. However, it's best to say 49 is the opening number of your area because that represents a private network or in a private area, and theoretically should not route to any other network that's out there. So NSAP addresses, not too bad, right? Get the 3 pieces, the 00, the system ID, and the area. Remember, you're only going to have to assign one of those to the router because that will tell the router what area it's in and what system it is in that area. Now let's talk about how ISIS forwards packets around the network. It's different than the other routing protocols. All the other routing protocols that we are dealing with in this entire series are designed for TCP/IP. So they're just naturally going to look at the next hop addresses. They're going to look at the cost of the links, or if you're looking at EIGRP, it's got that composite metric and finding the best way around the network. But ISIS wasn't designed for TCP/IP. So it doesn't really look at IP addresses, I guess you could say. Well, it roughly overstated, but it doesn't really consider the IP network. Rather, it's looking at the OSI routing domain. See, let me draw a mini network diagram up here. Let's say you've got all these areas, and you've got these routers in the area, you know, and that links off to some other area over here, or chocolate chip cookies, whatever you want to call them. But we've got all these different devices that are connected here, right? They're all communicating in their area, and they can reach the other area. But when it comes to routing, think ISIS and shift your mind over to OSI. You have to think that this is a routing protocol that was never really designed to carry TCP/IP in the first place. It was designed to work with OSI. So what will happen is all of the routers will build an OSI routing table, finding the best way to get to all of these neighbors in their area. And then the routers that have level 2 databases or backbone databases will start finding the best way to get to other OSI networks in the other areas. Now remember, I'm talking totally OSI. IP addresses have not entered the picture yet. So if I'm this router right here, I'm going to find the best way to get to router 4 over here based on saying, okay, well, I know there's router 4 because I see some of its hello packets, or it's in the link state database, and I need to find the best way to get to router 4 and add that to my OSI routing table. Now, again, OSI routing table, not IP routing table. So they're going to do that. They're going to build a whole topology of this OSI domain, learning how to reach every OSI router in your autonomous system, in your entire enterprise. Okay? All of that is separate from TCP/IP. All of what I just said has nothing to do with an IP address. They can find that. They can find all the routers. They can find their neighbors. They can find everything just based on that NSAP address, based on the OSI protocol that's running underneath your router. Okay, so ISIS will check, or sorry, I'm blending it in here. The IS, the router, will check a packet's destination. If it is in a different area than itself, it will route it based on the area address. Meaning, let's say router 1 right here gets a packet and it looks at that NSAP address and the packet is destined to 49.0003, which is this area over here. Immediately the router stops. It's like, hey, I don't need to look any further because that is in a different area. So let me, and I don't want to continue that statement because I'm going to blow my bullets down here if I do. It will route based on that area address. If it's in the same area, let's say, router 1 gets a packet that's destined to 49.0001, which is its same area, and it's going to go, oh, that's someone in my area, so let's look at their system ID. Whatever system ID they have, and then find the best way to get to that system. Find the best way to reach that other router within its area. Now, how they do that is different depending on who you are. If you are a level 1 router, remember, level 1 only knows about its own area, the inter-area packets, things that are destined for another area, are going to be sent to the closest level 1/level 2 router. Now stop right there. So router 1 is going to look right here. It's going to get some data, get some packets, and it's going to say, okay, I'm going to 49.003. That's not in my area. And because I'm a level 1 router, I don't even know about that area. I don't know who that is or how to get there. So what I will do is try to find the closest level 1/level 2 router based on the costs of the links and get it to them, because I know the level 1/level 2 router does know about other areas and can get me there and reach elsewhere. The way I think about that helped me out when I was learning this is I thought, hey, that's kind of like a default gateway. I mean, it seems weird, but that's how it works. It's like router 1 has a default gateway. If it's not in its area, then I'm sending it to my default gateway, which is going to be that closest level 1/level 2 router based on cost that it's going to find. Now, the intra-area packets are going to just be routed based on the level 1 database. Remember, level 1 routers know what's in their area, so they can reach all the other systems based on their system ID. Now, if you are a level 1/level 2 router, a backbone router, you know it all. You know about other areas. You know how to reach them. So any packets that you receive, whether they're inter-area or intra-area, you know how to get there. And you're going to be using your own databases that have all the subnets and have all the OSI information to move those packets around the network. Now let's talk about how ISIS communicates. What sort of packets are sent between the neighbors that form on the network? The first thing that we have to get by is another terminology change. Remember, we've changed total protocol suites here. We're not running TCP/IP, we're running OSI. And in OSI, there's no such thing as a packet. A packet is known as a PDU, which is a protocol data unit. In TCP/IP, we're used to calling things at the network layer a packet. And instead of calling them a packet now, we call them network layer PDUs. Or things at the data link layer, we used to call them frames. Well, we simplify it and we call it data link layer PDUs. So everything becomes a PDU and there's no packet, frame, bits on the wire. There's no segment at the transport layer. Everything becomes a PDU, and inside of those PDUs, we communicate between ISIS neighbors with 4 types of messages. First is the simplest, and that is a hello message. Hello message being the foundation that forms neighbor relationships, allows neighbors to communicate and make sure it's a type of keep alive that keeps those neighbors online. We have link state packets, which take the place of OSPF's LSA, the link state advertisement. So link state packet contains an update about a network or networks. You can have multiple updates inside of a link state packet. Those are I would say that's the core of the communication between our ISIS routers. Just like LSAs comprise the core of OSPF, and we would send an LSA anytime something changed or a network was added, we send LSPs in the ISIS world. Now, the final two are the PSNPs and the CSNPs, the partial sequence number PDU and complete sequence number PDUs. Those are used for a variety of things, but I'll boil it down real simple and say a PSNP is typically an acknowledgement. If you need to acknowledge that you've received an LSP, you'll respond with a PSNP. That's their number one purpose. The number two purpose is to request information. For example, if you have missing information from your database, then you're going to send a PSNP saying, hey, just give me this LSP, this information that I'm missing in my database. Now, the question is, how would you know it's missing? I mean, how would a router really know it's missing information? And that is that would be known because of the CSNP, the complete sequence number PDU. That, I almost said packet type, that PDU type is a summary of everything in the ISIS database. Sound familiar? It should be. It's the OSPF DBD packet. Remember the DBD, the database description packet from OSPF, is a summary of everything that's in the OSPF database. And then it's up to the router to get that summary and start sending link state requests, or LSRs, to say, I don't have this, I don't have that, and OSPF would send LSAs as a response. Same thing here. If you're familiar with OSPF, you're familiar with ISIS. The routers will send CSNPs out, which is a summary of all the link state packets that are in the database, because all those link state packets have sequence numbers. And the router looks at it and says, oh, I got that one, I got that one. You know, they're like trading cards. I got that one, I got that one. It's going down the list and it's like, oh, I don't have that one. It's going to send a PSNP to the router saying, give me the info. I don't have this update. So the router responds with the link state packet that has all the information. Problem solved. All the routers will then have a synchronized database. I wish ISIS would have won. I have to say that at this point. I wish it would have won the battle between OSPF and ISIS and taken over the world because it's so simple. We're covering in like 2 videos what would take us in OSPF 4 or 5 videos to cover, just because everything has become so simplified and boiled down. We looked at the packet types, you know, just 4 of them. We don't have LSA types and, you know, different kinds of LSAs. We just have 4 basic packets. And if you were to look inside of one of those packets in this architectural view, you find out it's really simple too. Right up front, you have the header. The LSP header, link state packet. And inside of there, it contains the PDU type. It tells what kind of PDU it is. Is this an LSP? Is this a PSNP? Is this a CSNP? You know, those types we just talked about. Is this a hello packet? It has the length of the packet, the sequence number of the packet, and the lifetime of the packet, because every single sequence number is given it's a timeout period, meaning after this amount of time, that packet is no longer considered valid if you haven't heard an update about it. And by default, that's 1200 seconds. You don't need to know all that. That's all just sitting in the header. That's all just the base information of the packet. After that header, if you were to open this in Ethereal, a packet sniffer, just to see what's going on, you would start seeing TLV fields, stands for type length values. All these are little shells, little carrier portable things. Like you've seen Tupperware containers, right? That's what these are. They're little Tupperware containers that go after the link state header. And inside each Tupperware container, inside each TLV, is some other information about ISIS. For example, and these are just some examples I put up here. You might have one that contains the IS neighbors, what neighbors it knows about. If you have authentication turned on, you have a Tupperware container that has all the authentication information. There's other ones that are in there that contains the ES neighbors. If you are running, you know, the OSI protocol on your end systems, the stations. There's a ton of just these little Tupperware containers that contain the information that makes ISIS work. One of those TLV fields that you see over here is a Tupperware container that contains attached IP subnet information. That's how they tweaked it. That's how they modified ISIS to work with TCP/IP version 4. Because they just created a Tupperware container that goes inside the packet. ISIS is just doing its normal thing, routing OSI, getting around the network. But at the very end of the packet is just a little Tupperware container that, if you open it up, has all the information about the attached IP subnets on the router. And the Cisco routers are programmed that when they see that Tupperware information, they open it up and they go, oh, that's IP stuff. That's going to go right over here in the IP routing table. So ISIS, here's what I want you to see. The original ISIS and the integrated ISIS, the one that runs for TCP/IP, are not that different at all. The original ISIS routed ISIS and routed the OSI protocol and found the best way around the network for the OSI protocol. Integrated ISIS routes the OSI protocol, finds the best way around the network for the OSI protocol. Oh, and by the way, attaches these IP subnets and corresponds them to the OSI protocol. Take a look at this packet. I mean, this packet in the header somewhere is going to be, who this came from. It came from the router with the NSAP address 4900031111, a system ID, blah, 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 dot 00. And that's going to be in that header somewhere. And somewhere in the end of that packet will be a Tupperware container that has all of the subnet information that is attached to that router. Now, the Cisco routers are smart enough that they get that packet and they go, oh, okay, well, I can reach that guy via OSI, and then go, oh, and I can reach all of these IP subnets on that router as well. It just ties the IP information to the NSAP address of that router. Since the routers all find the best way to reach that NSAP address, they inadvertently, it's almost like, oh, bonus, they find the best way to reach all the IP subnets on that router by the NSAP address. Does this make sense? It's pretty cool. It's how it works. And that's what made ISIS so flexible when IP version 6 came out. This was one of the first routing protocols to be released for IP version 6 because they didn't need to change much. All they needed to do was add a little you can see I've got little ... here because there's more TLVs than what I have here, but they just added a Tupperware container for IP version 6 information. Slight little tweak, no protocol standard changes or anything like that, just a new TLV field, and now we're routing for IP version 6. That is pretty hot. I should make mention at this point that OSPF had to be completely re-engineered for TCP/IP version 6. We'll see OSPF version 6, or I should say version 3, the next flavor of OSPF that was created, and it's a complete scrap and restructure. The whole protocol is different. So let's move into the ISIS network types. Last couple things I'm going to talk about here. The ISIS network types are simple. As it's been all along. There's no point-to-point, point-to-multi-point, NBMA mode, broadcast mode, all the modes we talked about for OSPF. There's just two. There's broadcast and there's point-to-point. That's the two kinds of networks that ISIS is engineered to support. The broadcast mode assumes that you have full connectivity, as in all the routers are connected, they can all reach each other. That's typically used for Ethernet subnets. You can also use that for like an NBMA cloud where you have a full mesh design. The broadcast mode will elect something known as a DIS, a DIS, a designated IS, which performs the same role as the DR/BDR did when we were in the OSPF days. There is no backup designated IS. There's just one of them that maintains the information for the subnet, so all the neighbors do not need to exchange routes with each other directly. They all just form a relationship with this DIS who maintains it for the whole network, just like the DR did in OSPF. Now, when you're dealing with NBMA networks, highly recommended that you use point-to-point subinterfaces and point-to-point network types as your network design for ISIS. If you try and tweak broadcast to work in an NBMA cloud, when you don't have full connectivity, it gets messy. It can be done, but it's very messy, it's very ugly. So it's best to just use those point-to-point subinterfaces. That's the best design for frame relay and ATM anyway. Just have one point-to-point subinterface per neighbor, and ISIS does the rest. Now, when you are in a broadcast environment, you will use multicast messages to reach each other. When you are in point-to-point environments, you will use unicast messages, which go directly between the neighbors. Regardless of whether you're using the point-to-point or broadcast style network, after the neighbor relationships have formed, we need to keep the databases synchronized. Remember, this is a link state routing protocol, so all routers in the same area have to have exactly the same database. They do that by it's simple, as always, by simply exchanging the LSPs. The link state PDUs are sent across to each other that contain, well, everything, all of the information that they know about. The IP subnets, the OSI routing information, it just shoots between the neighbors until their databases are synchronized. Now, we did talk about the two other packet types, and this is almost a little review because I jumped ahead of myself when I talked about them before. The PSNPs, the partial sequence number PDUs, are sent out as number one, acknowledgments. So as those LSPs are being sent that say, here's the information about the network, PSNPs are being sent back saying, got it, got it. Got it. They're just little acknowledgments for ISIS. This does not run on top of TCP, so it has to have its own acknowledgments or reliability mechanism. The other thing that it's used for is to request missing LSPs. It knows they're missing because of this final packet, the complete sequence number PDU. Oh, I said packet, didn't I? I meant PDU. The complete sequence number PDU is sent once every 10 seconds in a broadcast network. Now, it is a small packet. It just contains all of the LSP sequence numbers that exist in the database. It just says, hey, LSP 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's what our network consists of. So when a router gets that, it says, oh, this network has, or this area has LSP 1, 2, 3, 4, 5, 6, 7, 8, and 10. It goes, well, wait a sec. I have LSP 1, 2, 3, 4, 5, 7, 8, 9, 10. I don't have 6. So it will send a PSNP saying, hey, I don't have 6. And some router's going to respond and say, here's the LSP that is fully explaining what sequence number 6 is all about. So to make sure everybody's synchronized on a broadcast link once every 10 seconds, you can tune that up because that is a pretty liberal timer. It's pretty frequent. That just makes sure that if you add a new router to the network, it knows what's going on very quickly. It's only sent once in point-to-point networks, and that's when the link goes active. So it figures if it's a point-to-point network, there should only be 2 neighbors. So if it sends it once, that should be enough, right? Because there's only one neighbor, nobody else is going to be added. So there is no extra traffic that's being used, and it's very bandwidth savvy on those point-to-point networks. So that's the scoop. That's all there is to the ISIS concepts. After this, we're just going to dive into the configuration of ISIS. Now, I am giving ISIS a little more credit than is due because we did talk about things as they related to OSPF. So I know sometimes I walk away like, man, like after I finished talking about all this, I thought, man, why isn't everybody using ISIS? It's so simple. But then I remembered, like, when we talked about the DIS, the designated IS router, I didn't really go into depth because you already knew what the OSPF DR was. And you don't really need much more explanation other than to say the DIS is the same thing as the OSPF DR is to ISIS. But if you didn't know about OSPF, I would have had to explain that whole thing as well. What a DIS is, being that central point of contact and all that. So I guess I am giving ISIS a little too much credit for being simple, but it's still really simple. we talked about, just to wrap things up in this video, understanding the NSAP addressing, looking at how we can assign an address to our Cisco routers, just one that tells them what area they're in, what their system ID is, and then that 00, which designates them as an IS router. We then talked about applying that to Cisco routers by looking at a network diagram, to seeing kind of the architecture of ISIS, how we would engineer a network. We saw how ISIS routes packets. That was where if you're a level 1 router and you get a packet for a network in another area, don't pass go, don't collect 200, you immediately find the closest level 2 router, level 1/level 2 router. So we talked about how those packets are routed. We then talked about the packet types, or I should say, wink, wink, PDU type, because there is no such thing as a packet in ISIS. It's all PDUs. We saw the four of them. I almost said LSU, the hello packet, the LSP, the PSNP, and the CSNP. Four packets is it, and that allows ISIS to synchronize. Finally, we looked at ISIS network types, only two of them, point-to-point and broadcast. I hope this has been informative for you, and I'd like to thank you for viewing.